Well, here we are. Hello and welcome to Transform 2021. Welcome to this SEGY-SAK 2-hour tutorial that Tony Hallam is going to present for you. I just have the pleasure to introduce Tony to you. He's originally from Australia. He's a geophysicist with 10 years experience in the oil and gas business. And he's currently completing his PhD at Heriot-Watt University in Edinburgh. He's working on seismic history matching. He's been using Python for the better part of 15 years, and he's been the lead dev on SEGY-SAK, which he's going to present to you today, since its introduction at the Transform 2020 hackathon last year. So with that, I'll invite Tony to turn on his camera and microphone, and I will hand over to him. The stage is yours.
Thanks, Rob. Good morning, everyone, or appropriate greeting wherever you are. Today, as Rob kindly stated, I'm going to be running through the SEGY-SAK tutorial that I've developed for this particular conference. And it'll probably take the better part of the 2 hours. I might run a little bit over, but if that's an issue, you should be able to catch back up on the YouTube channel. So I'll just share my screen. Okay, hopefully you can all see that. So the first thing I'd suggest is that if you haven't already managed to clone the repository with the tutorial up and running. This will just start a live notebook session in the browser that you can use to follow along. It takes about 4 or 5 minutes for Binder to boot up, so I suggest you do that now, and by the time we get through the introductory notes, you should be more or less ready to follow along. There'll be limited interaction from me to you during the tutorial itself. I'll be keeping half an eye on the Slack channel, see what kind of questions are coming up if you have any. And I also have Valentin, who's available in the Slack channel to help you if you have any kind of teething issues getting started. Yeah, all right, let's get going. So the first little session here, we're going to cover a few different things related to SEGY-SAK. Just kind of talk about what the library is, give you a little bit of a tour of the resources that are available to you, kind of talk a little bit about why SEGY-SAK or where it fits into the ecosystem. You know, I get a few questions about why to use it. And then I'm going to briefly talk about the structure of SEG-Y files, because it's kind of fundamental to understand the way SEG-Y files work if you want to load them correctly into the package. So simply put, SEGY-SAK was developed primarily to make my life easier when it came with dealing with SEG-Y data. There are a few packages available that allow you to read SEG-Y data into Python, but the data structures that come in are not always easy to use or ready to go. So SEGY-SAK kind of acts as a bridge between SEG-Y and Xarray, and basically provides the SEG-Y data to you in a data structure which allows you to edit and manipulate the data in a meaningful and simple way. It was developed primarily at Transform 2020 last year, so it's a real privilege to now be talking to you about the package. It's matured quite a lot over the last 12 months. Hopefully people are using it with their day-to-day work. I'm also, as Rob mentioned, the primary developer for the package. and the primary maintainer at the moment. So I have a few people helping and raising issues and so forth, but I tend to be the one contributing most of the working code right now. I do use the package a lot in my own PhD projects. So I do a lot of synthetic seismic modeling. So it's really helpful to be able to generate synthetic seismic data and then export it directly to SEG-Y for loading into packages like Patrol and so forth. After this tutorial, if you've got any ideas or you're interested or you have issues, I'd strongly encourage you to raise them either in the Slack channel or on the GitHub repository itself. I'm always happy to hear how people are using the library, things they're having trouble with or things they want to do. All right. Okay, so the tour. There's a few locations you can go to get help with SEGY-SAK. The first one is the repository itself. And this is just under me and then SEGY-SAK. In here, we've got all of the source code, obviously, and a bit of information about the package and how it works. This is also where you should come if you want to contribute or make edits or in particular to raise issues if you're having any. We've also got some documentation on Read the Docs, which is built on a regular basis. This is a good place to start if you're just learning how to use the library or you want to know how to do something in particular. There's a quick overview, but generally I recommend you come and check out the example section. There's lots of detail here that you can look at in terms of understanding what the library is capable of doing and the types of outputs that it can provide you. And these examples are all available as Jupyter notebooks, so you can download them and play around with them if you want to. And then the last section I sort of point out is the API reference. So when you get a little bit more comfortable with the library, you can come in here and get some quick information about the call signatures of some of these functions that are available, as well as the help documentation related to them. We also have a dedicated channel on Slack called #SEGY-SAK. This is just in the Swung Slack, and I'm always generally available at the moment. People have questions or want to raise issues or ask for help. All right, SEGY-SAK versus X. So a lot of people ask about SEGY-SAK versus SEGY-IO, and SEGY-IO is a fantastic low-level library that allows you to easily load a lot of different SEG-Y data into Python relatively easily and quickly. But what SEGY-SAK does is it abstracts a lot of that lower-level detail that SEGY-IO requires to try and make it as easy as possible for the user to load the data. So the idea is that we want from SEGY-SAK a one-line SEG-Y loading function, whereas with SEGY-IO you would have to essentially interface with the SEG-Y file directly and manage the loading of all of the different aspects of a SEG-Y file from the text to the headers to the data itself. So that's kind of where SEGY-SAK fits into that part of the universe. And then when we talk about Xarray, SEGY-SAK is basically an extension to the Xarray package. So we build upon a lot of the good work that was done to develop a robust and detailed data structure that allows you to perform, quite a lot of complicated tasks in very few lines of code. And the Xarray data structure, data sets in particular, sit very well with 3D SEG-Y data. So we offer this bridge essentially between SEGY-IO and Xarray by allowing you to easily load data into Xarray data structures from SEGY-IO, from SEG-Y, and then export back to SEG-Y from that same data structure. So we provide those details. On top of that, we also provide a number of utility functions that allow you to basically perform common manipulation tasks to seismic data, and to ensure that the loading of that seismic data is correct. All right, so let's talk a little bit about SEG-Y files. They were developed a long time ago, back when SEG-Y seismic data was essentially recorded onto magnetic tapes. And those magnetic tapes had a very limited storage capacity. So the format was kind of developed as a sequential read format and a sequential write format that could be split across multiple tapes. And the result of that is you end up with a data structure that kind of looks like this. You've got this optional tape label, which is rarely used these days, I think. You've got then a number of data blocks defined by a specific byte size that have different amounts of information in it. At the front of the file, you've got the textual file header, often called the obsidic, which was the encoding format used for it. And this generally contains just sort of string information about the data that is contained within the file itself, as well as potentially information about where information is stored within the headers. You then have kind of like a global binary file header, 400 bytes in size, which contains information about the sample rate, the sort order of the traces, and so forth. Later on, with the Rev2 file format, they introduced this extended textual file header. It's not often used, but SEG-Y is capable of handling that. And then you then have basically the data, which is split into a sequential series of headers and trace data. And within the 245 byte trace headers, you'll have all the information that you need about the geometry of the files. So the trace numbering, the X and Y location, the inline and crossline number if it's 3D, the offset if it's gathers, and so forth. So all of this kind of needs to be essentially read in and then converted into a single unified data structure that we can use within Python. And in the most useful sense, we need to maintain this relationship between what is in the trace headers and what is in the data itself, because this allows us to understand and locate our data in space when we're trying to use it and interpret it. Okay, installing SEGY-SAK is pretty basic. It's available via the PyPy package manager. So it's just pip install SEGY-SAK. If you are running the binder today, you won't need to do this. This has already been done for you. The demo data we're going to be using today is a subset of the Volva full stack volume, which was made available by Equinor in 2018. So thank you to them. And if you have got the binder open, see if I can find it. Hopefully binder has kind of prompted you to get to a page like this. And you can just open the tutorial by hitting T21 SEGY-SAK. Oh. I think my binder has, here we go. Should open a page like this. So one thing to remember when using binder today is that it does kind of time out if you don't use it after 10 minutes. So if you find that the kernel restarts, you might have to rerun a couple of the cells further up the page to follow along. I'm not going to be showing you a lot of this supporting text that's available in the notebook itself. We're going to be concentrating primarily on the code cells as we run through the tutorial. But if you scroll down, we're basically about to start using SEGY-SAK itself from this code. So to check that everything's working, we can just try and import the SEG-Y loader. There's a little warning here because we're using TQDM to get some pretty loading bars within the notebook, but that's not a big deal. If everything's okay, you should have just executed the cell and we're ready to load some data. Before we get to that, though, we'll need to import a few different packages that we're going to use. The top three here are all just kind of system related, but SEGY-SAK interfaces pretty closely with Pandas, NumPy, and Xarray. So we're going to need all of those, and we're also going to need the matplotlib plotting package to look at our data. So just run that. And you can check to make sure that the data is currently available to your notebook by running this cell, making sure that the SEG-Y exists equals true. Okay, so that was the basic introduction. In the next section, we're going to be talking about some of the basic usage of SEGY-SAK. And then we'll move on to some basics with Xarray datasets. So a dataset is the structure that you get back when you load a SEG-Y data through SEGY-SAK. And then we'll end by talking about NetCDF files, which are the native save format for Xarray, and how you edit and save your data when you work with it out of SEGY-SAK. Okay, so to inspect files, we offer a few different methods. They're basically called SEG-Y header scan, SEG-Y header scrape, and SEG-Y text head, get SEG-Y text head. And all of these essentially allow you to do either minimal or full analysis of the metadata that is associated with your SEG-Y file. So this is your text headers, and your trace headers, and those fundamentally are the most important parts of the data set to understand when you're loading SEG-Y data correctly. So we'll bring those in. We can look at the SEG-Y text header by using get SEG-Y text head, and this essentially is going to return a string object which we've given some pretty printing here, so you can kind of see what's available in that text header. Text headers are 3200 bytes, so in this case you get 40 lines by 80 characters each, and here you can see it gives you a whole raft of information about what's actually in the SEG-Y file, including some useful data about where in the headers different types of information are located, so that can be really important to note. We can also do a quick scan of the trace headers. So often it's enough just to look at the first few thousand traces to work out what's going on. In this case, the SEG-Y header scan function allows you to basically pass in the file path and then the number of traces you want to scan. And it's going to return a data frame which contains some statistical information about what's going on. Now, one thing that happens with Pandas is it likes to kind of abbreviate your tables, which can be a little bit annoying. So if you're not aware of it, Pandas has this context manager, which allows you to increase the number of rows that you display after you've done one of these scans. Now you can see basically we've got a lot of information now about what's in the different trace locations. To explain what's going on in this table, in the first column, you've essentially got the SEG-Y enum name for that particular byte location. So all of these are kind of specified within the SEG-Y standard, and this is the name that SEG-Y uses for those particular byte locations. You've also got the byte location number, And you'll see these aren't sequential because most of these byte locations will be occupying 4 sequential bytes. So they should be stepping up in batches of 4, essentially. The count here is 2000 because we scanned 2000 traces. If there wasn't 2000 traces in our file, then this would be lower. And then we can look at the distribution, the distribution of those values that were scanned. And we can see many of these are actually empty. So there's actually no data in any of those locations. The CDP, though, does have some information. So we're going from a minimum of CDP 2150 up to 2351. We can see that the X and Y locations are in 73 and 77, but also it looks like they're in 181 and 185. So we've basically written those header locations twice. And we have some inline and crossline numbers here in 189 and 193. So all those numbers are going to be kind of important because knowing those byte locations allows you to load the data correctly. The other thing we can do, which can be sometimes quite useful, is to scrape the headers. And essentially this means we're going to load all of the information that's available in the trace headers into a single data frame. And this allows us to do a number of things, which we'll get to later on. The interesting parts of the SEG-Y header scrape method call are that you can also do a partial scan if you want to. So you can just get the first few traces if you need, and you can turn off the loading bar if you prefer. You can also pass in any key arguments to the SEG-Y open call as additional keyword arguments here. So if you have special requirements, including what do they call it? Big endian or little endian type requirements or different encoding requirements, those can be passed through. When SEG-Y-SAK scrapes the headers, essentially it returns a data frame. And this is basically all of the same values that we saw previously, the SEG-Y enums for those trace headers. If we look at what's actually in that data frame now, we can see that we've basically got all of our records. So in the index column, we've essentially scanned 12,322 traces. We've got 89 different header locations, many of which are 0 again. But we can also see that we're populating those columns where data was present with the actual values, which is what we wanted. To give you an idea of the inline 3D values, crossline 3D values, we can also have a look at what's going on there. So we can see those are all kind of coming in all right. It can be a little bit difficult to look at all of this information, particularly when you've got a huge number of traces on a big volume. So one way that you might choose to look at it is through plots. It's pretty straightforward to take that data frame and generate some interesting plots of what's going on in your data set. You can see here that the inline direction is our slow direction. We're sort of incrementing in a stair-step type fashion, whereas the cross-line direction is kind of oscillating backwards and forwards within each of those inlines. We can also see that we haven't really got any kind of outliers within the CDPX and CDPY. So everything is kind of loading the way we expect, which is great. So that's sort of looking at the header information. Let's talk a little bit about the loader itself, because there's a lot of functionality associated with a single line loader that kind of needs to be explained. When we look at a lot of the arguments that are available to the SEG-Y loader, not all of them are necessary all of the time, but there are some key ones that I'm going to run through later in the session. Obviously, you need to provide the SEG-Y file, so the path location of the file that you want to load. And then you can load either 2D or 3D data by specifying the byte location. There are some defaults provided for these, but if your data does not have information in those byte locations, it will generally just be loaded as 2D data. So if you find that your 3D is coming in as 2D, you may need to go back and look at your header information, your trace header information, to understand where exactly your inline and crossline numbers are, so that SEGY-SAK can work out how to convert your sequential SEG-Y file into a cube, essentially. We can also load gathers, so there's an option here to specify an offset byte location. So if you have 2D gathers or 3D gathers, those can be brought in. And you can specify the domain, so the vertical domain. So if you want your vertical axis to be depth, then you can say depth, or usually it'll load as two-way time. There's some other options down the bottom here, which I'm going to run through soon. But all of these essentially allow you to reduce the amount of data that you're loading in one step. So if you need to load a smaller or subset of your data set, you can essentially do that from the SEG-Y load kind of command. Okay, so I know that for this particular Volva file, the default values of the SEG-Y loader are appropriate. So it's really just as simple as putting the SEG-Y file path into the loader, and we'll basically get back a data set. Now, two things have happened here. The first thing is that we get these two kind of loading sequences. The first one is actually doing the SEG-Y header scrape action. So in this instance, we need to understand the geometry of our data set before we can create a data structure that we can then load the seismic data into. So the SEG-Y header scrape is an action that has to happen ahead of the actual data loading. Once that's been resolved, we can then load the data directly into that data set. And what you get back is an Xarray data set. If you're not familiar with an Xarray data set, essentially it's a collection of different data variables that can share common dimensions and has basically labeled coordinates. So in this instance, we've loaded a 3D data set, so we get back the dimensions inline, crossline, and two-way time. We can see that our data variable here has those same dimensions. And we also loaded in some header information related to this particular data set. So we've got the CDPX and CDPY values, which occupy the inline and crossline dimensions only. So these are constant for two-way time, so we don't need to define them across the whole data cube. SEGY-SAK also helps a little bit by loading in additional information related to the source file itself. You get a copy of the text header basically, and some information about the sample rate, the source file, and the coordinate scaler. And these additional attributes can be useful when you're trying to re-export the data back to SEG-Y, and sort of carries them forward for you, so you don't have to worry about them too much. We'll talk a little bit more about this Xarray data set in a few slides. So let's quickly take a look at the data and see what it looks like. The Xarray datasets provide you with a number of very helpful functions which allow you to essentially subset and plot your data quite quickly. We'll go through a few examples of these, but essentially in this one, I'm just going to select a single inline dimension. We're going to take the data array, transpose it so that we're looking at it the way we expect to see seismic data, and then plot it with the y-axis increasing down the page. And then we have some additional kind of plotting commands here, which create something interesting. That's it. So essentially, we've loaded in some seismic data. Xarray takes care of a lot of the plotting detail for us. So we've got the cross-line numbering, the two-way time, the inline that we're looking at, and a color bar now that is split because it sort of understands the type of data that we're looking at. We could, for example, decide to look at a cross line instead here by just changing up selection. And so we can see now that we've got an alternative view of our data set. So let's talk a little bit about some of the other keyword arguments that you can supply to the SEG-Y loader. We can obviously specify the key dimensions specifically. So these are the byte locations of the things that we need to load. You might remember, for example, that CDP trace headers. So I think the X was also in 77, 73 and 77. We could also specify to load from an alternative location if we wanted to. We could change the domain of the volume to be depth. Okay. So now we have depth as the vertical dimension instead. And you can see that we've still loaded the appropriate X and Y because we had that duplicate in terms of where information in the trace headers was located. And we can also ask for additional trace header information to be loaded. So in this case, I've just specified essentially a dictionary with a byte location. 117 just contains the sample rate, so it's not particularly interesting. But if you have important byte information in your trace headers that you want to bring in when you load your SEG-Y information, you can just specify this mapping essentially for the extra bytes fields. And that information will come in as an additional data variable that you can then use with your data set as normal. You can also do kind of filtering of the data set as you bring it in. So you can specify, for example, an inline and cross-line cropping. What essentially happens here is SEGY-SAK will do the entire SEG-Y header scrape, and then it will filter the traces that are loaded based on the inline and cross-line cropping values that you want. So in this instance, we just want a single inline to be loaded, and a windowed cross line that goes from 2000 to 3000. So this is going to be a single line essentially that gets loaded in. The entire scrape still happens, but instead of loading the full 12,000 traces, we're just loading 202. And the reason it's 202 is because the range for the cross line on that particular inline only goes from 2150 to 2351. So this is another way that you can kind of limit the amount of data that you're loading in. So if you just want to look at a single inline and you've got a very large seismic volume, this can be a way to reduce the amount of data that you load directly in a single line. Another interesting way you can go about this is you might have noticed that every time you go through this process, you've got to rescan the trace headers. And that is not a super efficient way to do it if you want to, quickly load one inline and then another inline. So you can actually pass the output of trace header scrape. If you scrape the full headers in one go first, you can then pass a filtered output to the SEG-Y loader to get information that you want. So in this instance, instead of using the cropping keyword argument, essentially we use this head_df keyword. We pass it the trace headers, and we're going to just filter those trace headers by selecting a subset. In this case, everywhere where the inline is less than or equal to 10,100. So you'll notice that that first loading bar is gone because we provided the appropriate trace header information to the SEG-Y loader, and we've told it specifically which traces we want to load. So now only 2,000 of those 12,000 traces were loaded, and we can see that our inlines cap out at 10,100. So this is kind of like a pretty neat way where you can use the trace headers pandas data frame and all the power that pandas has to filter that down to get specifically the parts of the data set that you want when you're doing kind of limited loading of the volume into Python. There's a few other useful tools that you might want to know about. The first one is the SEG-Y converter. So rather than convert or loading directly into memory from disk, so taking the SEG-Y file and loading it as a data set in memory, this function will look at the SEG-Y file, create an on-disk NetCDF4 file, and stream the SEG-Y data directly into NetCDF4. So we're going to talk about why you might want to do that in a few slides, but essentially this is a way to avoid having to assign an enormous amount of memory for large SEG-Y files if you want to convert them to a Python-friendly format, essentially. We have a function called SEG-Y freeloader. This is a little bit experimental at the moment, but it seems to work pretty well. If you have odd or complex data sets that don't fit the general mold of 2D, 2D gathers, 3D, or 3D gathers, maybe you've got azimuth information that you want to account for, or you've got seismic data that goes beyond the dimensionality of just being within the sort of interpretation realm, then you can use the freeloader, and it gives you a lot of flexibility in terms of the way that you load seismic data into Xarrays. The only real restriction is that when you specify the dimensions, that they are orthogonal to each other. So you need to have labeling within your trace headers that allows you to put traces into an n-dimensional orthogonal space. And the last one here, we have essentially added support for Petrel SEG-Y data in a limited sense. So this leverages the work done by ODSU, where they've provided a Python library that is capable of reading and writing SEG-Y. So there is a part of SEGY-SAK now that allows you to load that SEG-Y data into the same data structures that we're using for loading the SEG-Y data. And in fact, you can go from SEG-Y to a data set and out to SEGY if you want to, or in the reverse direction. Okay, I'm just going to quickly check whether there's been any questions. I think we're all okay. All right. So let's talk a little bit about the Xarray data set and what it looks like and why it's sort of useful when we're talking about SEG-Y data in general. I've kind of borrowed this picture and edited a little bit from the Xarray documentation. But essentially, you can think about Xarray data sets as being this sort of n-dimensional kind of set of data variables. So you could have multiple cubes, for example, with a set of kind of coordinate information. So the trace headers usually. And those are defined essentially on the inline and crossline, while the data cubes are defined on the inline crossline in two-way time or depth. And you can add additional dimensions to this, as many as you want. So you could have offset and azimuth as well if you really wanted. And then you also have a set of kind of point data or objects, which we call attributes. And these are kind of additional metadata that are useful for defining what's going on within your data set. This is a really convenient way of creating strong associations between all of the different labels and dimensions that you may encounter within the seismic data. So if you've got an inline, you saw that you can just instantly subset an inline and you get the X and Y locations of that inline, you get the labeled cross lines, and you also get all of the attributes. So Xarray kind of lends itself really nicely to the SEG-Y world, or the seismic world, I should say. So the next step's going to be a little bit interactive. You guys are welcome to kind of follow along or just kind of watch. But essentially, we've got our data set, and we can kind of see how that picture sort of fits with what's going on now. So we have our dimensions. These were those lines. We have our coordinates, which were the CDPX, CDPY, for example, were the planes. And then we have our data, which was the cube. And we also have our attributes, which were the point data. And you can access any of these just by using the membership of the data set itself. So you can get the DIMS, for example, which is essentially like a dictionary, but it's frozen, so you can't change the size of it without applying a method to the data set itself. You've then also got the coordinates. So you can access those directly and look at those. And you have the variables. Variables. There we go. Which are all of the kind of array type structures that were used to define all of those different aspects. So you can see we got CDPX here, CDPY. Data should be in here somewhere as well. I think, yeah, so there's data. You can also access any of those particular values just by using the name itself. So we can get the I line. This returns a data array, which is what any kind of n-dimensional component of the data set is. This is sort of like the base component of Xarray, if you will. So there's the I lines, for example, or we can get the cross lines. You can even get the data if we want that. Again, it returns a data array, and we can see that this is a three-dimensional cube. If we want to access the attributes, they're essentially just stored in a dictionary. So we have this ATTRS value, and we can see what is available to us in that particular dictionary. We can just get the keys if we want to see what's going on. Or we might, for example, want the sample rate, so we can just get that. So it's a convenient kind of way of just grouping what is essentially a single data set with a large amount of metadata into a single structure that automatically kind of understands how everything is related to itself. Cool. Yeah. So we saw already that we can kind of make selections on the data set. When you have a data set, because your variables all have different numbers of dimensions, and they may not even exist on common dimensions, for example, you can't use like the standard NumPy kind of index selection. So we couldn't do something like this, for example, on the data set because it doesn't really understand the slice. You can do that on the individual variables or data arrays. So this allows you to do kind of index-in type selection. But generally a more convenient way to do this is to use the .select and the .iselect methods. So select allows you to use labels, essentially, to access different parts of the data set. So I think we had like 10100 was one of our inlines. So we can access a single inline just by passing in the name of the inline that we want. So this is super convenient. We can also pass in a list, for example, if we want multiple inlines. So we could get the next one as well. And we get two. And they don't even have to be contiguous. So we could skip one, just get the next one after that. You can create kind of custom ranges. And in fact, you can pass multiple arguments to select. So we could also ask for just, I don't know, range of cross lines, maybe, I don't know, up to 2160. This. So now we just get a limited range of cross lines as well. So you can kind of use the selection tool to easily access parts of your data set via the actual values that you're interested in. But let's say that you're not really into that and you actually want to select things based on the index or the actual number of the location. In that instance, you can just use iselect. So in this instance, if I pass 10100, it's going to give me an index error because there aren't 10,000 I lines in this particular volume. But if I want inline number 10, starting from the beginning, then I can get that one. You can also do similar things to what you did with select and use lists or sets to access different parts of your data set. So that's all kind of pretty straightforward. The nice thing about this process is that when you do this selection, it does that selection on all of the variables in the data set. So not only is your data sub-selected, but also your X and Y and your inline and crossline. So now you have, for example, just a limited range of values rather than what you had previously where you had the full data set. The other thing I'd just point out here, I think I forgot to point this out on the last slide, is if you want your data array as a NumPy array, then you just put the dot values on the end and it will return a data array, a NumPy array that you can use in any other process. And in fact, Xarray data arrays can be passed into any kind of NumPy function and should work as if they are a NumPy array, which is really cool. All right. Oh yeah, so this was on the next slide, sorry. Yeah, you can get these as a NumPy array. Xarray datasets and data arrays also come with a large number of useful functions. So we've seen the plot one already, which allows you to plot information. The list is kind of endless, but some of the big ones that I use are interp, so you can do interpolation onto points, and not just points associated with the locations of your data, but points in between. You can calculate things like the mean, min, and max. You can transpose based on labels, not the current order of the data sets. And one of my favorites is actually broadcast-like, which allows you to avoid situations where you need to rely on mesh grid, for example. So let's take a quick look at one of these. Transpose is pretty cool because we can specify the order that we want based on the labels of the dimensions. So in this instance, we've now transposed CDPX in this case to be cross-line inline, but we could reverse that, for example. It should be the other way. And when we return the values, NumPy array of this, it will be transposed appropriately. You can also ask, for example, for the min and max, and these are all man-aware, so you'll always get an appropriate value back. With interp, it's probably easier if I talk about eyeline. With interp, you can select essentially a location somewhere within your cube, and Xarray will go away and do a quick linear interpolation to that location. Now, linear isn't always suitable for seismic data, but it does allow you to do kind of quick looks, especially if you're doing sort of like arbitrary traverses and so forth. When you want to do something a little bit more specific, SEGY-SAK has some helper functions within the accessor, which we'll talk about, that allow you to extract arbitrary traverses a little bit more easier. And broadcast-like allows you to essentially take any variable and make it look like it's on the dimensions of another variable. So we could take the eyeline, for example, broadcast it like the data set, like the CDPX, I think. So in this instance, we now have inline on both the inline and crossline direction, and you can see it's kind of numbering appropriately. So if you need to do operations that rely on knowing the inline together with another kind of map-like value, or even the cube itself, you can transform what was stored as a relatively efficient one-dimensional array into a three-dimensional array that can then be used for mathematical operations. So that one's pretty awesome, actually. Okay, a big one with Xarray is a variable assignment. So because Xarray needs to understand the dimensions that your incoming data set belongs to, you need to kind of specify those dimensions going in. So the available dimensions we have are inline, two-way time, and crossline, but you can actually specify new dimensions on incoming data if you want to. Let's, for example, create some blank data here, which is just an empty data set with the shape 61, 850, and 202, right? The same as the dimensions of our data set. We want to assign this in. If I just pass it like this, I'm going to get missing dimensions error. So we need to tell Xarray how this relates to the dimensions that we already have in the data set. And the way that's done is just to specify the dimensions as a leading tuple for the incoming NumPy array. So 61 was the I line, 850 was the two-way time, and 202 was the cross line. So now we can specify those dimensions going in. And if we have a look at the volume, we can now see that we've got an empty data set here, or a data variable with the dimensions. Now you can see that the ordering of the dimensions here is slightly different to the data set. That's not really a problem for Xarray. It kind of understands the ordering. We could have kind of altered this, or we could do a transpose operation on the size NC volume itself, try and make all of these align. But because the dimensions are labeled, it's not really that important to Xarray what order these dimensions are in, as long as they're labeled appropriately. You could also, for example, bring this volume in as a on a different dimension. Oh, wait. Let me just. So we could specify that blank now exists on the depth dimension rather than the two-way time dimension. You can see that we've added a fourth dimension to our data set, and our blank data set now belongs to the depth dimension rather than the two-way time dimension. But they share a common inline and crossline, so they're still sharing X and Y locations and inline and crossline numbering. Okay. So a few quick questions about Xarray that commonly come up. And the first one is, why don't you make the global coordinates the dimensions? So, for example, why don't we make X and Y the dimensions that we index along? And the simple reason is that Xarray requires you to have orthogonal dimensions in your data set. And the X and Y dimensions are generally not orthogonal, or the global coordinates are not orthogonal, because our SEG-Y data is often rotated relative to the local Cartesian grid, right? So the only way to really handle things, and every geophysicist will know this that works with seismic data, is to work in the local grid, which is inline, crossline, and vertical. SEGY-SAK helps you with a few of the coordinate-related problems, like selecting traces based upon coordinates through the accessor. So there are a lot of functions available through the dot size accessor that allow you to select information using coordinates rather than inline and crossline local grid coordinates. And the last one here is, how do I save or persist changes that I make to the data set? And that's why we're going to talk a little bit about NetCDF. So the NetCDF file format is a file format that was developed primarily out of climate science, because they have a large amount of multi-dimensional data related to things like wind speed, cloud cover, temperature, so forth, as well as time, obviously. And it's a binary format. It's generally very fast, particularly with Xarray, and it provides a form of lazy loading. And what that means is essentially that you can get all the information you need to about the file, about the Xarray data set itself, without loading the entire volume into memory. So you can leave large amounts of the information on disk, and Xarray has sophisticated programming in the back end that will only load the data that you ask for at the time that you ask for it. So that's lazy loading. Interestingly, Xarray data structure is actually modeled on the NetCDF file format. So there's a very easy link between NetCDF and Xarray itself. So a common thing that I often do is I'll work in NetCDF when I'm using seismic data in Python, because I scan the SEG-Y once, or I convert it directly to NetCDF, and then I can come back to it over and over again without having to worry about loading and converting the data into memory. That lazy loading is also really useful for very large files, particularly because it integrates well with packages like Dask, which is used for large parallel kind of computational tasks. Okay, so I think I kind of already answered that question. The main reason is it fits well with the current Python ecosystem, much better than SEG-Y. It's a more performant data type, and it's relatively widely used. So even if you convert your seismic data to NetCDF just for your project in Python, there are other languages where NetCDF is also implemented, like Julia. There's a big C package available for it. Pretty sure you can load it into MATLAB as well if you want. So from that perspective, we're almost able to bring SEG-Y to pretty much every language, because more people implement NetCDF for their language than they implement like a SEG-Y reader for their data set, for their language, sorry. Okay. So to persist your data set, it's really this easy. We offer what's called an accessor. So this is a namespace created by SEGY-SAK within the Xarray dataset class. So you just do the .sizeIO, and then there's a number of methods in here that you can use to write out information. But to go to NetCDF, we just call to NetCDF, and this will write out data, a size NC data set. I mean, you can put whatever extension you want on here, but I usually just put .size NC because it tells me that it came from SEGY-SAK. And we can just check that data set is there. So you can see now we've written out this this data set, and it's a lot bigger than the original SEG-Y because we added that additional data to it. So remember, we've now got the blank values, and this is float 64, so it's actually going to be twice as big as the data itself. So you can store multiple kind of volumes within a single file if you want to, by going through this process. And it's pretty straightforward then to reopen that data. So from SEGY-SAK, you import the open size NC method, load it up, and come straight back in. And it's pretty much instantaneous because it's doing that lazy loading. So you don't have to worry about going through the process of doing a scan. Okay, saving back to SEG-Y. I think this is the last section before we take a break. So we provide from SEGY-SAK the SEG-Y writer function. Again, let's have a quick look at the help. It's not quite as complicated as the loader, but there's a few things you need to provide. The first is you can provide the size NC, which is either an Xarray dataset in memory or a string pointing at a size NC file on disk. If it's a size NC file on disk, then we'll stream the data back from size NC to SEG-Y. So you can avoid memory issues using that process. You've also got to then specify the path of the SEG-Y file you want to output. Any information that you want to put from the coordinates, essentially, or the additional variables into the trace headers needs to be specified through the trace header map, which is a dictionary. By default, we're going to try and output CDPX, CDPY, inline and crossline if you're 3D, and CMP if you're 2D. But you can specify additional locations to write things. The chunking argument here is to do with how you bring data from that SEG-SAK file on disk into memory and then out to SEG-Y. So this allows you to specify the size of the chunks that you want to write at in one time. We'll kind of get into that a little bit later today. And then you can specify, for example, the dimension that you want to write out on. So it's possible to have data existing on both two-way time and depth. So sometimes you might want to specify specifically which way you want to output your data. And then the last one here that's kind of useful is use text. So essentially, if you've got some text information that exists within the SEG-SAK or the Xarray dataset, that will be written out directly to the SEG-Y file. If this is off, then it'll write a default EBCDIC that SEGY-SAK creates for you. There are a couple of attributes that you need to make sure are present before you write out to SEG-Y. The first is the coordinate scaler. And this is because SEG-Y headers are all 4-byte integers. So if you want to preserve the sampling of floats, then you need to scale that information in some way to make it an integer. You also need the sample rate and just to specify the source file. And this is usually available, or it can just be set to be blank. So then we can just write that out. In this instance, I'm going to put the inline in a funny location. Oop. Yeah. Oh, right, because I added that blank dimension. Hold on a second. Okay. So this is another kind of neat thing you can do with Xarray. You can just quickly drop a dimension if you don't want it. So let's do that. Now this is going to write out to SEG-Y. We can also write additional variables, like I said, with the trace header map. So in this instance, if I've got value XY, so just existing on the inline and crossline, you can see that it's float 32, so it's going to be truncated to some kind of integer if I don't do any kind of scaling to that. But that can be written out to a particular byte location, in this case 13. So if you have these custom kind of bits of information that you need in the trace headers, then it's possible to, all right, because I've got to again. Okay, that's written out. So let's see what we got. Remember, this is the SEG-Y file that we just wrote out to. So if we do a quick scrape, we can have a look. So we can see that XY here got truncated to an integer, but it's written into that byte location 13, just like we asked for. All right. So I think now's a good time to take a 10-minute break. I think we're going well. We're probably going to go past 11, I'd say, at this pace. But if you have any questions, drop them into the Slack channel, and I'll check them out and see whether I can answer them when we come back. All right, so we're back again. Hopefully you had a good 10-minute break. There's been a couple of questions in the chat. Richard asked about whether or not Xarray supports 3D interpolations, and the short answer is kind of. If you want to do simple nearest neighbor or linear interpolations, then you can start to do things in 3 dimensions and up. Unfortunately, they don't really support kind of complex interpolation types beyond that. If you're doing 1D or 2D interpolations, then you can use the spline type interpolator, which comes from SciPy. For seismic data, you could potentially write your own type of interpolator if you wanted to, and we'll kind of talk a little bit about how you apply functions to sort of subsets of your data later on in the tutorial. Doug was asking about whether or not you would put large volumes through the SEG-Y converter first to NetCDF. And I think it kind of depends on how much you intend to use the data after you've converted it, because obviously converting basically duplicates the file on disk. If you just want to look at little bits of the data regularly, you don't need the whole volume in memory, or you don't want to process the whole volume, then you might be better off using filtering of the trace header scrape, for example, to access subsets of your large SEG-Y volume. Graham suggested there was some problems with streaming really large data files for memory, and I think I'll have to take that one offline with Graham and work out what's going on there, because we should be able to move large SEG-Y data across to NetCDF. There might be some logic problems going on there. All right, moving on. Let's move on to kind of the meats of the session today. The next few sections are all going to be about how we can use data in this convenient Xarray dataset structure to perform kind of common seismic interpretation and manipulation tasks. So to begin with, we're going to talk about horizon extraction, and essentially what we want to do is we're going to take some point data and interpolate it to our cube dimensions. And then I'm going to show you how to kind of create some maps from that information. And finally, we're going to end with how you can then use that information and the interp function from Xarray to essentially extract amplitudes along that horizon. So I've provided a data file here which contains some point information for the top huge information, which is actually the top of the reservoir at Volva. And we're just going to check that exists, no problem. And then we're going to take a brief look at what it looks like. So we'll just look at the top 5 lines. And we can see that it's just a simple kind of space delimited file where we've got an X coordinate, a Y coordinate, and a 2-way time, which is, you know, pretty standard fare for surfaces or seismic interpretation. Sometimes this might also be an inline and crossline, and that would also make our lives pretty easy in terms of relating it to the seismic data. But if you get it in X and Y, then we can read it in just using pandas. That's probably the simplest way. And we get the 3 columns now in a table. So nothing revolutionary about that. But if we want to then convert that pandas data frame, which is tabular data, to a 2-dimensional grid that we can relate to our seismic volume, we provide this surface from points method. and it's contained within a second accessor for X-ray datasets provided by SEGY-SAK. So we have the dot size namespace, and this is where all of the seismic related methods rather than the IO related methods are generally located. So we pass in our data frame. We can have a look at the call function here for this particular method. You can see we've got to give it some points. In this case, that can be a data frame, or it can be a NumPy array of X and Y values or pairs. We then have to specify the attribute that we want to interpolate back to our seismic grid. So in this case, because we have the data frame, we're going to give it the column name that we're interested in. So if you loaded in multiple columns, you could do this multiple times. This could also, if you'd passed in NumPy points, X and Y pairs, then this would be a one-dimensional array of the same length as the pairs containing the Z values. And also, because this is a data frame, we're now going to specify the way we're going to relate the X and Y coordinates. So the columns CDPX and CDPY from our data frame that are going to relate to the CDPX and CDPY in the size NC volume. So this is basically going to match those two sets of labels together to do our interpolation. And we're just going to use linear interpolation because that should be fine. These points are pretty close to the locations of the traces. So if we run that, that's going to go away and come back. And what it provides us is another data set, but it doesn't contain the seismic data. In this sense, it just contains the interpolated horizon. And this has exactly the same geometry and dimensions as our seismic data set. So we've quickly taken X, Y, Z points and interpolated them to a horizon that now matches exactly the dimensions of our seismic cube. We can create a few maps of this information, just again by using the plotting interface from Xarray. So that's really easy. We just select the variable that we're interested in this case, the horizon, and then we call the plot method. Because it's 2D already, it just knows what to do. We don't need to do any selections or anything. And this will plot based on the local grid. So here's the inlines and cross lines. And you can see we've got kind of like a bit of a high here and some lows because we're talking about two-way time down, right? Often it's more convenient to plot this in terms of the global coordinates. So we're interested in the X and Y kind of positioning of this data set. I'll show you a few ways to do this. There's no right or wrong way per se, but because the CDPX and CDPY are not the dimensions of the horizon, but more like a location information, we can't use the dot plot method out of Xarray anymore. So we have to get a little bit more manual here. And we've got essentially a P color mesh now with our X and Y grids, two-way time grid, all of these converted to NumPy via the dot values method. And you can set the aspect here to 1. So we're looking at square to square dimensions. And now we can see that the horizon is actually quite different in terms of its sort of scale and location. And so we've got this rotation, which is actually the rotation of the seismic cube itself. Another way to go about this is to use an affine transform. So an affine transform is essentially a mathematical operator which relates your local grid to the global coordinates. And if you have a 3D volume, SEGY-SAK has another function within the .size accessor, which allows you to essentially create an affine transform going from inline crossline to CDPX and CDPY. And you can get that transform just by calling the get affine transform method from the accessor. This probably won't work if you have skewed or non-square data sets, so just keep that in mind. We kind of rely on understanding where the corners of the data set are and ensuring that the inline and crossline are actually orthogonal to each other. But again, now we can just pass the inline and crossline. In fact, we don't even have to put the dot values on, because remember, Xarray data arrays can be interpreted as NumPy arrays by pretty much anything. And then I've had to transpose the horizon here, because obviously the ordering of the inline and crossline wasn't quite correct. And we can apply the affine transform now just by taking the transform we got from our Seismic cube and adding it to the axes existing transform. So in matplotlib, axes usually have an affine transform that they're using to go to the plotting coordinates. So by adding these two together, we kind of get things appearing in the same place. And essentially, we get the same thing. But the nice thing about using the affine transform from the seismic data is we can do other things like this. So we can take, for example, an inline. We know that 10100 was one of our inlines, and it kind of spanned this sort of sub-range, 2200 to 2300. So we're just going to plot a line. But by passing the transform information, we can actually plot that inline over the top without having to worry about converting those inline and crossline coordinates to the global coordinate space. So that's quite a neat kind of process that you can do to relate the seismic local grid to the global grid when you want to plot things in the real world. Okay, let's move on to vertical section views. We can add our horizon data back to our seismic volume just by adding it as a variable. And we don't have to specify the dimensions of the variable in this case, because we're adding it as a data set, or as a data array. So if I just show you what this looks like, the horizon was returned to us as a data set because it had a lot of additional information. But if we just select the data variable to a time Huygens, then we can see that this comes back as a data array. And by the way, it's probably worth pointing out, you can also access these as keys. So this will return the same thing. So you get a data array back, but it already has some implicit dimensions associated with it. So when you pass this into the seismic volume, it actually understands where to put it. So now we've got basically this additional data variable in our seismic data set, which contains information about where the seismic horizon is. But remember, because we're about to do some subselection of this data set to plot a section view, we're also going to subselect the seismic horizon. So we get the two together essentially in one go. I'm just going to quickly here drop that depth so it doesn't cause any more problems going forward. Now you can see we just got rid of that blank value, which I used for demonstration purposes earlier. All right, so let's plot some data in a horizon. So the first thing we're going to do is we're going to take a subselection, And we only need to do this once because we're going to subselect both the seismic data and the horizon, which now belongs to that data set at the same time, simultaneously. And then we're going to create essentially a new figure that we can add that data to. And we're just going to do the dot plot option for the data itself. I'm just going to turn this last line off here so we can see that we get just the seismic data. We've also subsetted the vertical time range here so that we can see what's going on. And interestingly, I've added this method nearest because I don't know exactly what my sampling on the vertical dimension is, but what Xarray will do when you pass this selection method is if you don't know exactly where you want to locate something, but you select nearest, it will just pick the closest matching line, which is quite good. So if you've got a regular kind of line spacing, you could say, well, just give me the one closest to 10.101, for example, and it will pick, you know, like 10.0100 or 10.0102, if those are the two that are available. And then to add the seismic horizon, which is what we're trying to do, we can just, again, plot a line. And the x-axis here is the cross line, right? So we're just going to pass that as a cross line. And the name of the horizon variable was Hugen. And we're just going to set the color to black. So now we get a nice looking seismic horizon, which exactly fits the seismic data that we're plotting at this time, because we're taking the sub-selection together. So that's really, really convenient a lot of the time. Okay, seismic amplitude maps. So to get an amplitude map, it's seriously one line. And the way you do it is by using the interp method, which essentially relates the data array and its coordinates. So in this instance, we're going to sub-select based on two-way time. And we're saying that the two-way time that we want to sub-select at is the horizon. And what the interp method will go away and do is relate the coordinates within the Hugen horizon data array to the seismic volume that we're interested in, which is the data part of SEG-Y vol. And in this instance, we're just specifying linear interpolation. That will extract an amplitude map. So pretty quick. Let's see what it looks like. Again, we're just doing some pretty basic plotting tasks here, so nothing too revolutionary going on. But when we plot that up, see that we've now extracted the seismic amplitudes along that horizon. We can go back up and check that. I think we were looking at a line through here before. Do we think that, yeah, so you can see like on this part of the line, we're basically in the positive range, whereas on this part of the line, the horizon's kind of following the negative range. And that sort of translates to what's going on down here. So that's pretty much single amplitude or single point horizon extraction. If you want to do windowed extractions or horizon sculpting, there's a tutorial on the SEGY-SAK documentation website that shows you how to do that. So shout out to, it'll come to me what his handle is. But yeah, that was created as part of last year's Transform event. And I think a lot of people have found that useful. All right. I'm going to move on from horizons now and talk a little bit about mapping functions over blocks. So a common operational task that you need to do with seismic data is you want to process traces individually, or you want to process chunks of data within like a rolling window or something. We're not going to do the latter specifically today because that's probably a tutorial on its own. But I will show you how you can apply functions to traces within an Xarray data set in a couple of different ways. You can think of this, I guess, as kind of like a type of trace maths, I suppose. And the example I'm going to use to demonstrate this is horizon flattening. And if you're not familiar with horizon flattening, essentially imagine you've got a 3D seismic cube with a surface intersecting it, usually seismic interpreted horizon. If you take that cube and adjust the time samples of the traces so that all of the points where the cube intersects that surface occur at a constant time, you're essentially flattening on that horizon. So you're trying to move data up or down to ensure that that surface is flat. And essentially to do this, we need to basically combine what we did previously with the adding the horizon to the cube. And we need to introduce a function that allows us to resample the seismic data to a new time axis, essentially. All right, so like Pandas, Xarray has tools that allow you to perform grouped operations, so-called group by. And this essentially allows you to create subsets of your data based on some kind of variable or categorical information. So in this instance, for example, we can loop over all the inlines in our data set. I'm just going to show you one here. By calling group by and passing .iline in as the value or the dimension we want to loop over. So in this instance, you get back the name of the group. So that's obviously just the first inline in the data set, and a new data set that is essentially subsampled at the by taking a selection of the input data set, the size and cvol, at that group. So this would be the same, for example, as calling size and cvol dot select inline equals 10090, right? But what Xarray does is they provide a convenient iterator, so you can do this for every inline in your data set. To apply group by to each trace individually in the data set, we actually need to create a new variable that allows us to identify each trace individually. And the simplest way to do that is just to assign a new variable, which we're going to call trace, that is a range as long as there are traces in the data set that we're reshaping to the inline and crossline dimension sizes. You take a look at what that now looks like. You can see we've just basically got a sequential numbering of traces. So when we apply the group by operation and it takes the selection, it's just going to give us back a single trace. So we can test that now. We're going to do group by over the trace. Let's see what we get back. Trace number is 0. Okay, that's fine. And everything's been reduced. So we just have these two dimensions where there's only one in the inline crossline dimension, but there's this all of the time samples. So that's fine. You can see that it's kind of created this multi-index here that allows us to say where we are, because we're doing quite a large dimensionality reduction to get to this point. But that's fine. All right, so horizon flattening. when we apply a function to our new kind of trace subselection, we're going to essentially pass it that new subset. And then we need to think about what part of that subset we're going to use to flatten on. So in this case, horizon var is just going to be a string telling us which data variable we're going to use for the current time at the flattening time on that trace. And then the last thing that we need here is we need to specify the output sampling two-way time. This is probably the most complicated bit because Xarray won't allow you to have multiple traces on a single dimension sampled differently. So if we could do that, it would be simple enough to just subtract the horizon time at a given trace from the two-way time axis, and the trace would be shifted. But because the horizon is not sampled exactly the same as the two-way time axis, we actually need to specify what the output sampling should be that we want, and we'll sort of define that in the next code cell. We then create a quick copy of the data set because we don't want to modify the original, and then we shift the two-way time by taking the value of the horizon at the trace that we're operating at. So this now gives us an output two-way time, and we then can interpolate our data to the two-way time that we've specified for the whole cube. So you can think of this as being like the simple shift, and if you were just dealing with one trace, that would be fine. You could just return that and plot that up. That wouldn't be any issue. But because we need to reconcile all of these shifts across the different traces that we're shifting, we need to do this interp operation that will move the data set so that you get regular grid alignment in the time direction. Hopefully that's clear. To calculate what the flattened two-way time will look like, I won't go into it too much, but essentially you need to understand the maximum value of the Huygens horizon and the minimum value of the Huygens horizon, and then you work out after shifting what your minimum and maximum ranges will be, assuming that your horizon output time will be 0, essentially. So we're going to flatten to two-way time of 0. Oh, I better run these two. All right, so how does that work? Well, conveniently, Xarray has this operation you can apply to a group by object called map. And if you're familiar with the way mapping works in Python or Java or any language for that matter, essentially we're going to apply that function we defined, hflat, to each group, and Xarray takes care of the recombination for you. So this is called a group map, combine type operation. So the combine is kind of implicit at the end that all the traces that we operate over will be recombined into a single data set that we can then map. And we need to specify those extra arguments that we have for hflat because it'll only get the data set. So in this instance, Huygens was that name of the variable, the horizon variable we want to flatten on, which is contained within that trace that will be passed in to hflat, and we give it also the output two-way time range that we expect the data to be interpolated on. And this takes a little bit of time for the full volume, so I'm just sort of sub-selecting here for the single inline so we can move on. So that ran okay. We've now got this flattened seismic slice, and we can plot that up, see what it looks like. Here's the original data. This is the same plotting that we saw before with the unflattened seismic horizon. And then on the other side here, we're going to show the flattened seismic cube. In this instance, you can see that, yeah, we flattened to 0 time, so that horizon now appears at 0 time. And all of the data around that horizon have been shifted appropriately to kind of match where the horizon should be. So that's horizon flattening with group by. In some instances, group by is probably not the best way to go about things, particularly if your seismic data is very large. So more recently, Xarray has been improving their integration with Dask, and they've produced this function called map blocks, which is very similar to the map blocks operation that you have for a Dask data array. But essentially it allows you to chunk your data. When you chunk data, you're essentially defining the size of the data that should be considered as a single memory unit, essentially. And Xarray or Dask does some crunching in the background to basically load only what it needs at any given time before returning something to output. So to kind of chunk a data set, you just use the chunk method and you specify the size of the chunks that you want. So in this instance, we want just a single inline and a cross line. So we don't actually even need that trace numbering variable anymore. If I was to, I'm just going to show you what this looks like. You can see that a data set is chunked by looking at its print output. So in this instance, it's telling you that the chunk size is sort of 11850, and there's multiple chunks, and they even usually give you a nice little, scroll down, no, nice little picture of your chunked data set. When you specify the size of the chunk, that is the data set or the sub data set that will be passed to your map blocks function. So you call map blocks on a function, this function will be mapped over each chunk in your data set individually. So because we've specified each chunk as an individual trace, only an individual trace will be passed to hflat, will be passed to hflat to run their operation. Because this is a lazy, or map blocks and its integration with Dask is lazy, it becomes a little bit more complicated. You have to tell map blocks what you expect the output will look like if it's going to be different to your input. So in this case, I need to create a template, essentially, which converts the input data set to what I expect the output data set to look like. And this operation doesn't actually run. It just basically does the conversion of the coordinates and dimensions so that map blocks understands what it will return. And that's kind of like a fundamental part of working with Dask. So it's taking a little bit of time to run here, but essentially it's just creating tasks associated with mapping hflat over every single trace. Now, the interesting thing here is that I think TGMB isn't actually, run. So instead of doing the computation and then returning, computed values to you, when you chunk information, every operation that you run essentially becomes delayed. And that operation will only be executed when you actually ask the values that you want. So even though I've mapped this over the whole volume, I haven't actually had to run any computation just yet. When I start to plot the information though, and I ask for the data specifically, that operation will be run just for the data that I selected. So in this instance, you can see that that operation has essentially been applied to this information. But I don't need to worry about doing the subselection. I can just change to a different inline. Let's do that for both of those. And Xarray and Dask will take care of the operation for me. So that's quite a nice way of running a large operation and then being able to quickly check things just on a small subset of the data. Dask itself is quite a big tutorial on its own. So if you're going to go down that pathway, we might maybe organize something for another time. So a few final thoughts on map blocks. It's still under development. It was only kind of a recent addition, but I've definitely found it very useful, particularly for the types of operations we want to run. Remember that it's going to work slightly differently to Python's normal instant run result type paradigm. So you're getting everything back as a lazy object that hasn't actually been executed yet until you ask for the values specifically. And there are other delay-like functions that you can then tag onto your map blocks. So, for example, if you use the to NetCDF, you could output that delayed function directly to disk. There's tools like rolling, which allow you to apply a function over a window within your data set, and that also works in a lazy way if you need it to, and the same with interp. Okay, next section. A few times I've been asked about the vectorization of seismic data, and the clear reason for this is people want vectorized inputs to machine learning processes. It's not really useful to have seismic data in n dimensions when you're trying to do that, unless you're doing perhaps image type processes. And then they do some machine learning, and then they get it back, and they want to send it to back to SEG-Y so they can look at it in their normal package. This is the last section, by the way, so we should be finishing up pretty soon. So it's really easy actually to go from a seismic volume to tabular data. You can just use the to data frame method because you have this kind of direct link between Xarray and Pandas. In fact, Xarray was kind of originally billed as the n-dimensional version of Pandas. When you do that, you get essentially a multi-index data frame. So here's our dimensions: two-way time, crossline, and inline. And then any data that we have in the data set will be converted into tables. Pretty easy. In fact, your CDPX and CDPY will be automatically broadcast to be the same size as the largest, or the same size as all of the dimensions that they fit over, right? So that's really useful. You can remove the multi-index to make everything fully tabular by just using the reset index method. So now you've just got a trace number essentially, oh sorry, a sample number, not a trace number. And your multi-index is now available to you as a feature for anything you want to do. In fact, here you can see you've also got your horizon and your trace data. So you can kind of build your features in normal kind of n-dimensional space and then head to the tabular format when you're ready. Let's have a quick look at the info for all of these. You can see that by going from having a multi-index to actually explicitly specifying the index values from the dimensions that you do increase your memory usage. So it might be worth kind of keeping that in mind when you do this operation. In some instances, for machine learning purposes on really large data cubes, it might even be worth grouping by inline, for example, saving out data frames as HDF5 objects, and then you can use Dask operations, for example, to recombine those data frames when you come back in for machine learning, so you can create kind of subsets of the data quite easily. Right, so then you've done your operations, or you've done your modeling with machine learning, and you've got an output, and you want to go back to Xarray so you can output your data to SEG-Y. The first thing you need to do is you need to make sure that your dimension features are still in the data frame. In this instance, we know that inline, crossline, and two-way time are still there. And we need to set those as the index. And when you put them together like this in a list, it creates the multi-index again, which is fine. It's not really an issue that the ordering of these has been changed. That's fine, because Xarray will kind of take care of everything that you need to worry about. And then to take that multi-index back to Xarray, Pandas has the toXarray method, and it's really that easy. So as long as you have these dimensions defined correctly as the multi-index, when you come back, everything should be where you expect it to be. The few differences are that because we had to broadcast all of our information to fill the tabular data, all of our coordinate variables now exist within the full 3D space. So when you do this return to Xarray, you might want to limit, for example, the variables that you bring back at any one time, and then you can recombine them when you have Xarray data sets. Pretty straightforward. The other thing that will be gone is the attributes. So any of the attributes that you had in the original cube are going to be lost when you convert to the data frame. So when you come back, you'll have to reassign those attributes to make it possible to output the data to SEG-Y. So here we're just basically putting the same attributes that we had back into the data set that we brought from Pandas. We'll also need to kind of reset some of those coordinates once they come back in. I just did the full conversion, so remember these values are now 3-dimensional. We can reduce those to 2-dimensional by doing a mean operation along the two-way time axis. So this will just reduce them basically to 2D. So you can see what that does. Now CDPX and CDPY are reduced, and they need to be here in the coordinates as 2D for us to go back to SEG-Y. All right, so that's pretty much it. From there, you just use the SEG-Y writer and export the data. So that's pretty much the tutorial for today. If you've got any questions, feel free to drop them in Slack. I'm going to wait 30 seconds just now, have a drink of water. I can answer those now here on the YouTube. If you want to see a demo of the CLI, also let me know. That's the command line interface. So there are some tools you can use to interface with SEG-Y data directly from the command line if you prefer. All right, a few questions coming in now. What features would I say are missing from SEGY-SAK? I think there could be some better handling of the coordinates with Xarray, like the global coordinates specifically. There needs to be, I think, some more concrete examples available to people on how to use this package with really large data sets. You know, obviously what we've been doing today is with a toy data set, really, you know, just a few tens of megabytes. So once you get up into the gigabyte or even terabyte range, things start to get complicated really, really quickly. Ideally, it would be nice if there was an accessor for SEGY-SAK that allowed you to do the header scan perhaps, and then do selection tasks on SEG-Y data directly, so that you didn't have to always load in the information. You could kind of interface directly with SEG-Y. I've had a look at how to try and make the most of the data interfaces that Xarray has to NetCDF, for example, and they also offer interfaces to some other file types, but it's a little bit obscure to me, and I haven't quite had the time to go in and really work out what the best way to do that is, or even if they, you know, it might be a bit foolish to try and write something that fits into a lot of the back end of Xarray. It's probably better to have like an accessor that works specifically for us, but in an Xarray-like way. What else are we looking for? There's always opportunities for people to contribute their own examples, data, to help out with the documentation. Thanks to Richard, who's been doing a bit of proofing for me the last couple of days. And also, if you want to write your own accessor functions, I'm always happy to help people improve that part of the package. So if there are tasks that you're doing regularly and you think they might be helpful to other people, it's generally pretty straightforward to integrate that into the dot size accessor. So yeah, I mean, there's definitely a lot of things that can be done. I mean, the core of SEGY-SAK is always going to be loading and exporting SEG-Y data from Xarray. That was always the objective, but these other things are definitely nice to have. Ooh, the largest on-disk data store I've used. Probably been doing some things with volumes that were about 100 gigabytes, I think. But I don't do that regularly, not for my PhD. So if other people are doing that with SEGY-SAK, I'd be interested in hearing your stories and your pain points, because the challenge, I guess, is always to manage seismic data, which is, you know, prohibitively large most of the time. Anyway, I'm gonna call it there. Thanks to everyone who followed along. I hope you enjoyed the tutorial today, and I'll pass back to Rob.
Okay, well, thank you very much, Tony. Yeah, that was great, and I'm not a geophysicist, but we were chatting a little bit during the break, and I think for geophysicists, this is going to be awesome. It only remains for me to thank Tony, as I just have. I really want to thank the sponsors, Studio X in particular, who I forgot to mention in the introduction, but without them, this wouldn't be happening. And there's another group of people without which none of this would be happening, and that's the Software Underground community, of which Tony's been part for a long time too. So with that, I'll let Tony switch off, take a break, and then he'll probably join you guys in the Slack channel. And that's it for this tutorial. Thank you, and see you in the next one. Bye-bye.